I bet you must have used one of those trading apps on your phone. But have you ever wondered, how does this app actually work? How does the trading app on your phone make you trade with someone else some assets? There is an exchange. You place your order on exchange, and the other party places the order on exchange, and those orders cross each other, and then you have a trade. But how does that work? I'm Sonia, and you're welcome to C++ versus Rust. We will look into an exchange implementation in Rust. Once again, welcome. This is C++ versus Rust, and we'll be talking about Benthic. Benthic is my own implementation of an exchange in Rust. This implementation is very simple. I will demonstrate you on an example how does the exchange work. So this is my code. This is my test. There's a number of classes in Rust I have created to implement an exchange. But before we go down there, I want to show you how it actually works. So I can run this test and show you. So we can see that first we create an account for user 1001 and we create another account for user 1002. We also deposit to those users some assets. We deposit 2 Bitcoin at the price of $50,000 to user 1, and we deposit 20 Ethereum worth of $4,000 to user 2. Alright, so they have something in their sheets. The balance sheet of user 1 says 2 long of Bitcoin. The balance sheet of account 2 says long 20 Ethereum. So these are balance sheets of the two accounts. The balance sheets are managed by the margin. Margin is a special entity in this software that manages balance sheets and portfolios. So let's see what happens next. There is a message from user 1001, so that's user 1. It's an order, ID 1. So order from user 1, ID 1. Buy 1 Bitcoin at $50,000. So that's an order we receive from the user 1. And then we send to the user 1 a response saying we promise to receive 1 Bitcoin, okay, for this user. Right? So the user will be receiving this 1 Bitcoin. And then there is a market data update which says there's on the book an order of size 1 Bitcoin. This isn't very detailed information, okay? We should say as well the side here. But for this purpose of this log, it's sufficient. Then there is another order, also from user 1, the second order. The second order is to sell 1 Bitcoin at the price of 12.5 Ethereum. So that's on different market. This one was Bitcoin dollar, and this one is Bitcoin Ethereum. It's a different market, right? The quote currency is Ethereum, the base currency is Bitcoin. And here the base currency is Bitcoin, and the quote currency is dollar. All right, so user receives a promise, okay, that they will deliver 1 Bitcoin. So this user is selling, so they will be delivering 1 Bitcoin. And this is the order, okay? All right, so what's the balance sheet look like? So you would expect these two orders made a change to the balance sheet in some form of shape. However, they didn't actually change any balances because we didn't execute any orders yet. We have a special column saying open. Open means how much balance is open in the order. So account number 1 has open quantity of dollars, $50,000 on the short side. Because in order to buy 1 Bitcoin for $50,000, the user 1 will have to deliver $50,000 in order to receive 1 Bitcoin. So they will be short $50,000 potentially. It's potentially short, right? They're not short, but they are potentially short. Then they are long on 1 Bitcoin, potentially long. And they are potentially long on 12.5 Ethereum, right? Because, they'll be receiving Ethereum when they sell the Bitcoin. Okay? And then they are long on Bitcoin. They have 2 Bitcoin. These 2 Bitcoin came from the initial deposit. Okay? So they have 1 Bitcoin open on the long side and 1 Bitcoin open on the short side. The one open on the long side is one they receive potentially in the order to buy 1 Bitcoin. And the one on the short side is the one from the sell 1 Bitcoin. Okay? The account number 2 didn't change. They only have 20 Ethereum long from the deposit, from this deposit here. All right, let's see what happens next. User number 2 comes and the order 3. Okay, I'm just ordering orders 1, 2, 3, 4, 5, even though this is a different user and this could be 1, but for convenience of us to look into those logs, we know that order 3 is order 3. Okay, so we receive order 3 from user 2. They want to buy half a Bitcoin at 12.5 Ethereum. So they will be receiving half a Bitcoin and delivering 12.5 Ethereum. Okay, that's what they want. Now, what happens now is there was an order on the book. Remember, I don't print here the books, but there was an order on the book from user 1. There was an order to sell 1 Bitcoin at the price 12.5 Ethereum. Okay, and that order gets matched against this order from user 2 because they match, right? This order is at the same price, but it's half of that quantity, so they will match. It will take half of it. And we can see here how it gets actually matched and executed. We can see all the lots that are created or matched. So first we open a long position for user 2 on Bitcoin. Okay, because they're receiving brand new Bitcoin. They didn't have any Bitcoin, right? So you can see account 2 doesn't have any Bitcoin, has 0. So we open new lot of quantity half, because this is how much they ordered, right? So you can see on the right side which order this came from. This lot came from this order, buy half Bitcoin and 12.5 Ethereum, and it was executed at 12.5 Ethereum. So that's the price at which it was executed, because this is the price they ordered it, but the price at which it was executed can be better, right? This is how order books work. User 2 also closes Ethereum. You can see that we're closing Ethereum because user 2 had 20 Ethereum on the long side, and in order to buy half Bitcoin, they had to dispose 12.5 Ethereum times half Bitcoin. So that's 6, right? That's 6.25. And we can see that we're closing this 625 and the remaining quantity is 1375, right? Because it was 20, right? So we can see the original quantity was 20 and the quantity left on the lot is 1375. That's after the portion of the lot was closed, okay? And that's again the same order. So those are the 2 lots that were matched for user 2. But there's also lots matched for user 1 because the transaction is between the 2 users. So user 1 will close a lot of Bitcoin. Okay, so there was a lot of quantity 2 and quantity half Bitcoin is closed. So now we have left 1.5 of Bitcoin for user 1. And this is the order. You can see that this is a different order than this one. So you see, this are 2 different orders. They were matched against each other. User 1 had a limit order on the book. User 2 comes with an order which matches this order, right? So these are 2 different orders, but they both execute at the same price because they have to be, when there is a match, the price is 1, okay? So they were at the same price, the orders were at the same price. Later on in this example, I show you what happens when I send an order at different price. Okay, so let's see what happens next. So we close the lot half quantity on Bitcoin and we open 625 on Ethereum. We didn't have any Ethereum before, okay? So we open 625, we can see. All right, what happens next? We get the execution, right? We send the execution to user number 2, okay? So this was internal matching inside of the trading system. Margin is an internal component inside of the trading system. These two are the private messages sent from the exchange to the user so that the user knows that they have managed to execute this order. So there was two orders, user 1 and user 2. Their orders were matched. Both of these users need to get execution now. So you see, user 2 gets execution of their limit buy half Bitcoin at 12.5 Ethereum, and they get half quantity that was executed, right? So the order was for half, but they get half. So that's the same quantity. And they are the aggressor because they were the second one. It was their order that was matched against the one that's on the book. So they are the aggressor. And this is the execution for the first user, right? So the first user placed an order on the book. Okay, it was sell 1 Bitcoin at 12.5, but only half Bitcoin was executed, right? So execution says half was executed. So that's what comes in private message to user number 1. And then there is a market data. That's a public message. And the public message will say half Bitcoin was traded, okay? This is private details that would not be directly in the public message. I just show it here for easier debugging, okay? And then the order of user 2 is being cancelled afterwards. So for this order, the remaining quantity is cancelled because the remaining quantity is 0. Let's just, well, we could just not print this line because 0 is, that's the actual reason why it's cancelled, right? We don't place on the book 0 quantity. Okay, so let's look at the balance sheets. So user 1 had 2 Bitcoins and 0 other things. User 2 had 20 Ethereum. And now user 1 has 1.5 Bitcoin, okay? And that half Bitcoin went to user 2, and now it's in user 2 account on the long side. User 1 now has 625 long Ethereum, okay? They had 0. And user 2 has 1375, right? We can also see that the open quantity for user 1 has changed. It was 1 on the short side. Now it's half on the short side, okay? Let's see what happens next. User 2 sends another order, this time to buy 1 Bitcoin at 12 Ethereum, okay? So user 1 is selling it for 12.5 and they want to buy at 12. So there is no match. These orders have no match. So you can see that they get promise that they would buy 1 Bitcoin at 12 Ethereum in some future. Okay, promise means the order is on the book, it's waiting. And then there is a market update saying there's 1 Bitcoin, okay, for this order, okay? Again, this is just logging information. All right, so this is what happened when prices didn't match. The asking price for sale of user 1 was here, 12.5, and bid of the user 2 was 12. It's lower, so there is no cross. They don't match. Okay. Let's see what happens if the prices actually cross. So this is 12.5 of user 1 of the ask, and this is the bid of user 2. It's 14. It's higher price, so they match. Okay. So you can see that the user 2 is sending 5th order to buy 1 Bitcoin at 14 Ethereum. So that will be a match, and we can see a match is happening here by looking at the lots being created and matched. So you can see that user 2 receives 1 Bitcoin, okay? So it goes long 1 Bitcoin. And if I look at user 2 account, okay, they have now 1.5 Bitcoin. They had half Bitcoin, now they have 1.5, right? This is how much they received. Now they close the close long position of Ethereum, okay? They close and they left 125 on Ethereum, okay? So you can see that the user 2 has 125 Ethereum, okay? And the user 1 got 1875. So they had 625, okay? But they have received additional 12.5, and now they have 1875, okay? You can also see that on the account of user 1, the open quantity of Bitcoin now is 0. It was half, and now it's 0, right? So there is no more quantity open for user 1. Okay, and the user 2 account of user 2 has one quantity open of Bitcoin because of this promise to buy one Bitcoin for 12 Ethereum, okay, which wasn't realized. It's on the book, okay? Let's see what happens when another order arrives. So user 2 is now sending order 6, which is to buy one Bitcoin at 15 Ethereum. We cross book again, and what happens now, we open long for user 2, 1 Bitcoin, okay? So now user 2 has 2.5 Bitcoin. So that's another lot, right? User 2 is delivering 11.25, right? 11.25. It goes short, right? We open short lot. So you can see on the short side, user 2 has 11.25. So they're now owning 11.25 Ethereum, right? We can also see that user 1 goes short half Bitcoin because they had half Bitcoin. When they deliver that 1 Bitcoin, they're now short half Bitcoin, right? So that's our lots being matched. And now we have 2 execution reports coming to those users. We can see that aggressor, right? The user 2 was aggressor. They sent the order to buy 1 Bitcoin FT15. So the aggressor gets 1 Bitcoin executed, and the user 1, the order on the book, also gets 1 Bitcoin executed. The price of execution, right? The price of execution was 12.50 in this case, right? We can see from the lots here, it's executed at 12.50. Okay, we don't show it actually here in those messages. So this is the final balance sheet of those 2 users after all these transactions. You can see that the trading engine is quite complicated, right? And the way it works, there is a number of stages. Let's have a closer look at how this system works. This is our user. They send an order to order manager. Order manager finds a book for which this order is. Remember, when we send an order, there is a market, for example, Bitcoin, Ethereum. That's the book. That's the book of orders. That is buys and sells of Bitcoin for Ethereum. So once the order manager finds the correct book for the order, it tells the book to match the order against the entries in the book. And when the book finds a match, it goes to execution policy, and execution policy goes to margin, okay? So you can see here that the margin is managing those lots, right? So margin will decide, okay, so this is the user 1 portfolio, this is the user 2 portfolio. Now we have a match. We need to take some assets from one portfolio and give them to the other portfolio, okay? So margin does the job of going into portfolio, and inside of a portfolio of each of the participants, each of the users, it will find the assets that are matched in this order, okay? And when there is a match and there is sufficient amount of assets, or it is allowed to go on the margin, so this means going short, then an execution is allowed. When execution is allowed, we return to the user execution. And we can see these 2 executions here. Both users get the order executed, right? Because you need 2 orders to get them matched, right? Okay, so that's what user is receiving. But also, how would this user know that other people are trading? So the same way that other people know that this user is trading, from market data. So whenever execution happens, book sends to market data policy an update, and market data policy will publish those updates to the users that are subscribed to market data, okay? So that's our generic exchange design, you know, there is nothing really special about it. In the real exchange, you would have additional components. There would be some, you know, KYC checks here, some order validation and so on. I didn't implement in the margin any logic to say if we can go on the short side or not. It's just, if you're going on the short, you're just going short. So there could be a logic here in the margin to do a proper margin calculation. I didn't do a proper market data, publishing. So I just log that there happened an event that would result in market data event. But, this could be aggregated and published as a top of the book, depth of the book, and trades, and, the details of those events would need to be polished. Of course, the system isn't production ready. There is no timestamps. There is no useful order IDs whatsoever. So this is only a demonstration of how such a system can be implemented in Rust. Let's look into the code. All right, let's look into the code. So this is Rust. The first thing we do is we define some assets. So again, in production code base, you would probably have those assets in some database, and you would have some boilerplates to start the whole exchange. You would load it, you would create those things in some, factory of assets or something like this. So here we just have like this one simple example. So our asset dollars is an asset with symbol USDT and 2 decimal places, because dollars have cents. Cents are 2 decimal places. The second asset is Bitcoin, and we give it as 7 decimal places. Next is Ethereum, we give it 6 decimal places. So Ethereum is kind of magnitude less than Bitcoin in terms of price, okay? And then we have markets defined. So market is, for example, buy sell Bitcoin for dollars, right? So we say there is a base asset, in this case it's Bitcoin, and there is a quote asset, in this case it's dollars, okay? So I have those assets defined here, so I have dollars, Bitcoin, and I'm just saying that market consists of the base asset and quote asset. And if I want to know symbol, I will say base asset dot symbol, okay? And this is very useful because then I can say base asset dot decimals, okay? So note that I have decimals for assets and I have decimals for markets. And the reason for it is that when you look at the asset in isolation, you may have a different number of decimals, more decimals when you look at the asset at isolation, right? But if you trade an asset on a particular market, then the granularity of the updates on that market may be much lower, right? So you may have less decimal places on that market because of the, the period trading, right? So you have different decimal places for the same asset on the market and when you look on the asset in portfolio, okay? Across markets, same asset can have different decimal places. That's the whole point, because different markets trade different pairs. And the number of decimals for the market is specific for the pair. If you trade Bitcoin dollar, it's going to be different number of decimals for Bitcoin and dollar than if you trade Bitcoin and Ethereum, right? So there are the 3 markets here defined: Bitcoin dollar, Ethereum dollar, and Bitcoin Ethereum. Okay, and they have some number of decimal places defined. Now I have defined 2 order books for Bitcoin dollar and Bitcoin Ethereum. Okay, because these are the only 2 order books I'm going to be sending orders in this example. I have defined 2 trader IDs, 1001 and 1002. Okay, we have trader A and trader B. I've created this order manager, which has order books. So here we go, our order manager. Then I create margin manager, okay? So that's this guy. And in the margin manager, I add an account for trader A and trader B, okay? And to that account, I add sub-accounts for assets. So we say trader A will be having Bitcoin, Ethereum, and dollar sub-accounts. Okay, and then I do additional thing here. I transfer to one of those sub-accounts some deposit. So you can see I'm transferring here to Bitcoin. So the market is Bitcoin dollar, and I'm transferring to Bitcoin. This is the price at the moment of the transfer. So I want to just remember what was the price of the 2 Bitcoins at the moment I did the deposit. That information might be used later for P&L calculation. I need it right now only to store it in the lot, because lots have both the quantity and the price at which it was executed, right? And the price is in a quote currency. So it is dollar in this case. I do the same trick for the second account. I deposit some Ethereum, you can see. So this is 20 Ethereum at the price of $4,000. And next, I'm creating the execution policy using the margin manager. So this means that, well, I could have this execution policy execute always, which doesn't use any margin. So this execution policy could just say, yeah, it's a valid order no matter what. But I'm actually creating it with this margin, okay? So that execution policy will go to the margin to say, hey, could you check the portfolio before I do the transaction? So my execution policy is to log executions. So they just end up on the screen, right? And I also have log market data policy. So it will print on the screen all the market data updates, right? So then this guy. So whenever book sends an update to this policy, it should publish it to the subscribers. But in our case, it will just print it on the screen. And here I've got a list of orders. So this is an array with number of orders there. There's 6 orders here, okay? So you can see an order is just a structure with the market to which the order applies, the ID, the participant, which can be trader A or trader B, the type of order, okay? So let's see the type of order. I decided to use type enum for this case because Rust allows you to have these nice enum types with data in them. So I have order type deposit, withdraw, immediate or cancel, limit order, or market order. And you can see that the market order has different data in it than the limit order or immediate or cancel. Immediate or cancel is essentially a limit order that gets cancelled if the quantity isn't fully filled. So this means if I order 10, only 5 gets filled, then the remaining 5 is going to be cancelled. In a limit order, if I buy 10 and I only execute 5, the remaining quantity 5 will be placed on the book on the opposite side. But you can see they are both limit orders. You can see that the limit order differs from the market order, that it has a price. Market order doesn't have a price, okay? So this way, by having an enum, I will never get confused in Rust with the type of order I'm processing. If I'm processing a limit order, Rust will shout at me saying, hey, Sonia, it is a limit order, it has a price, you forgot about the price. Or if it's a market order, Sonia, there is no price in market order, you know? How many times have I had issues with orders in C# or C++ where there was price equals 0? Why? Oh my God. Oh, because it's a market order, or things like that. You forget about those things. Rust is super safe. Rust is safe, not only memory safe. Rust is business logic safe. By doing this, your business logic is safe. You have a business logic saying market orders don't have a price. Go figure. Right? So where do I get the price from market order? Well, from the matched limit order, which is on the book. And that actually came handy when I was implementing margin, which was reminding me about this little problem. We'll see it in a second. All right, so we have those orders here defined, and this is an array in our example. I have this little lambda here to just run through those orders. So it takes an order manager and orders, okay, a slice, and we'll just print I'm sending an order. So this is the part where we're just pretending we're this user. There is no component for the user. I'm the component for the user. And then there is this function here, lambda, for printing portfolio. So it does this nice printing of this balance sheet with all this, things, right? And this is our scenario, okay? It's very simple. You can see that the scenario is first, print the balance sheet after deposits, execute orders 0 and 1, print portfolio, execute order 2, then print portfolio, then execute order 3 and 4, print portfolio, and execute order 5, and that's it, right? Because there is 6 orders. So yeah, so this is our scenario. Let's see how it works when we send an order. So we have this local function here, execute order, okay, which will go over all orders that are in the slice, and it will tell the order manager to place an order, okay? So order manager here, in our example, is an order manager which takes order books, which are order books. So let's look at that. So we have the order manager, which takes a book manager, an RC to then order book manager. So order book manager is a trait, as we can see here. And it is implemented by order books here, okay? So the trait says that we have get order book, which gives us option of RC ref cell. Now, that's not really thread safe. We could use arc of read write lock, and that will be thread safe. Also here, the book manager is in RC and could be in arc, right? Let's look what place order is doing. Place order will first check if the book for this market exists. If it doesn't, we will error saying we don't have this book. And if the book exists, then we place order on that book, okay? Call place order. Let's check that one. So this is our implementation of order book. You can see what order book is. Order book is a simple struct which has associated market, bids and asks, which are price levels, okay? And the price levels has levels, which is an RB tree. So I'm using red-black tree, okay, for storing the levels in the sides of the book, okay? So that's to be super fast. And that one is an intrusive collection. Intrusive meaning that I'm not putting into this RB tree my levels. I'm making my levels part of the tree, okay? So let's see what is this price level adapter. So you can see that the price level adapter is generated by this intrusive adapter macro, and it takes this price level struct, which has a link RB3 link. So this is our intrusive link in this RB3. So the price level has order queue. Orders is a ref cell of the deck of order quantity. Okay, so what's order quantity? Order quantity is simply the quantity and RC to an order. Okay, so this is the quantity remaining on that order. Order has some quantity in the order. I order 10, but after a portion of this order gets executed, there's some quantity left that is unexecuted, right? So that's the quantity, and it starts from full quantity and it keeps going down like a progress bar. All right, so price level is an entry in intrusive RB3 using this RB3 link with orders, which is a queue of order quantities, okay? And the price levels, it just contains levels, which is an RB3 of those levels, okay? Let's see what happens when you call place order on the order book. You can see that the place order takes an order, the execution policy and market data policy, and then we match the type of an order. If it's a limit order, if it's immediate or cancel order, or if it's a market order, we do a different type of matching, okay? So let's pick one of the cases, okay? So if it's a limit order, then we create new order quantity with the quantity on the order. And then if the side is bid, for example, we match against ask, and whatever quantity is left, we place on the bid, okay? So if I'm sending buy order, that's a bid. But my buy order will be matched against the sell orders. So first I have to match it with ask, which is sell orders. So this is what I'm doing here. I'm matching it with the ask side, with the sell orders. And you see, I'm passing in the mutable reference to order quantity. So I'm expecting that this match limit order will change the order quantity, right? So if there is a match on the sell side, and my order was like buy 10, and it's now buy 5, right? So this new change will be in this order quantity here. And when I place it on the bid side, on buys, but I place this updated quantity, okay? So this is not a reference. Place limit order will consume this quantity, okay? You can see how I'm using these references and move semantics of Rust. For the matching, because matching has to happen before placement on the book, for matching, I'm using mutable reference because I want the order quantity to be changed by matching. But for placement on the book, I want to consume that order. because once it's placed on the book, I don't want this order to be mistakenly used for something. I don't want to match it afterwards by mistake. If I swap those in order, so if I did place and then match, it would not compile. That's again, a mechanism in Rust that prevents me from breaking business logic, right? Okay, let's see the match order. So this is a function match limit order, and it is on price levels, okay? So price levels is an arbitrary where each level has a queue of orders, of order quantities. But this says match order side because match limit order apparently is the same as match market order, except that there is a different operations for the market and for the limit that need to be done, okay? And this is our unique matching function. We don't repeat the code, okay? So we have this ops here, price level match ops. This is a trait. And by using this trait, I allow myself to have just one match function, which works for both sides of the book, okay? And it also works for any type of an order, okay? So if I look at the price match ops, so what is the price level match ops look like? It's a trait with begin ops, move next, and is finished. So begin is going to tell us where is the beginning of our arbitrary. Is it at the front or at the back of the tree? Because when you look at the sides, the bid side starts from the lowest price, goes to the highest price, and it is the highest price that's the top of the book for the bid side. So that's the end, that's the back of this arbitrary. But then for the ask side, also the prices go up because arbitrary is sorting them upwards. So the top of the book is the lowest price, right? So for the ask side, it is the front of the arbitrary. And we can see that there is implementations of these price level matchups for market orders and for limit orders. They are basically very similar. So the market matchups implement the begin as, if it's a bid side, we go from the back. So we go from the highest price down to the lower prices, okay? If it's an ask side, we go from the lowest price and we go higher and higher, right? So this is our move next as well. So where we said for the bid side, we go lower, 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 so move next goes previous. And this is our ask side, so go next is moving forward, higher and higher prices. For the market order, we finish when the quantity on the order is 0. So limit matchups have a limit price. The limit price is where we stop our iteration. We can see the implementation of the begin ops and move next is identical. The thing that changes is finished, okay? So of course, if quantity is 0 and there is no more quantity on the order, this is when we finished. But also, if we reach the price limit, so if we're on the bid side, we're going lower, 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 and if price is lower than our limit, we don't want to go further down, right? So if level price is below the limit price, we stop. And for the ask, it is opposite. So we go higher and higher and higher, and if the price is higher than our limit, we want to stop, right? So this is our matchups. So let's just look at this matching function, how simple this function is with these traits. So we start with a cursor, which we get from begin ops. So we know it's either front or the end of our, of our tree. And we keep going over next and next and next, whether this is higher price and higher or lower and lower, okay? So we get the current cursor position. We check if the price at this level telling us, and the quantity of our order left is telling us to stop the iteration, right? And if we're good, we match the level, right? So we go with the quantity left on this order and we go to the level in the book and say, hey, do you have any orders to match with this order, right? If level is empty after this whole matching, we would like to remove this level from the book, right? So we have this price, we have this book with, for example, ask side, we have increasing prices on those levels and say we're matching this next level and our order is quantity 10 and the order on this level is only one order, quantity 5. This is the last order, so this level goes away, and the next price level has some other orders. We can match against them. Okay. So here we go to the next level. So we go to the higher price level. We check if that price on the higher price level is beyond the threshold, and if so, we stop, right? So this is our very simple matching function, and you can see how easy to understand and follow this function is in Rust. Rust is not going to allow you to make any mistakes. Let's see match order for the price level. Price level has this order queue, okay? It's just a queue of orders. It's actually a queue of order quantities. So match order function for the price level will start from the beginning of this queue. So regardless whether on a bid side or on the ask side, a level is always starting from the beginning of the queue because this is just a FIFO queue. First order that came in is the first one that gets executed. And we go and consume those orders that are on the level. So this loop is simply consuming those orders, okay? We calculate how much quantity we can execute in this order. So on this order, in this level, there's some quantity, right? So you have, so order book has two sides. There is a bid side, okay? That's our bid side. And there is an ask side. And here, between the best price for buying and the best price for selling, it's a thing called spread between them, right? So if I'm having an order here and it's a buy order, it gets matched against the ask side. If this order is a sell order, it gets matched against the bid side, okay? So this is ask. And this is bid. Okay, so on this side there is levels here. So there is a level here, level here, level here, and as well on the ask side we have level here, here, and here, and so on. And on each of those levels there is some orders. There's one order, some other order, maybe bigger, maybe smaller, maybe bigger order, some other orders, some other orders, and each price level has some price. Let's say this one is $100. This one is, let's say, $200, just for illustration. And this one is $300, okay? And the same on the bid side. So you have some orders here, some orders here, some orders here, and so on. And this one is $90. This one is $80, and this one is $70. So if I have an order here to buy something, some quantity, okay? Let's say I want to buy some quantity 10. It's going to be matched against this level here, against ask side. And let's say the quantity 10 is not available on this level here. The total quantity from all these orders, let's say, is 5. This one is 1, this one is 2, this one is half, this one is 1. So that's actually 4.5, okay? So we're left with 5.5 quantity. So we go with this order to this next level and we match, let's say there is a 4 here and there is a 1 here. So we match these two orders. So this one buy order will grab all these orders, okay? It will be executed against all these orders, not just one. It will swallow all these orders of other users. If it was a sell order, it would be consuming the orders on the bid side. Let's say all these orders here, right? So this is what's happening here. We consume orders in the queue of one level. And if we consume all the orders on this queue, the other loop that we're looking at will remove this level and will jump to next level, right? So the quantity we get executed is the quantity of an order on the book versus my order quantity. As we said, if I'm ordering 10 and on the book I have 1, then quantity executed will be 1 at this stage, okay? Now, the next stage is very important. So we already did a match. This is called match. We have a match between two orders. my quantity was bigger than their quantity, so there was some lower quantity that will be executed from my order. But we need to check if this execution can happen. So execution is actually a complicated thing because it's not, this is just a match, and it's not just a match. Execution is a mechanism to actually make things happen. So let's go into execution policy. So our order came from our user to order manager, where it went to the book, and it's now going to execution policy because we have a match. Let's check this one. Execution policy is a trait. There is an execution policy called execute always, and this execution policy only complains if quantity is 0. Okay. We have another execution policy. We have an execution policy for margin manager. Okay. So this guy is implementing execution policy. So this thing is actually our logging execution policy. We can see it here, it's log executions. And it is a decorator of an inner policy, okay? So margin is also execution policy. So the design we have here is that we have this execution policy that we're using with our order matching, and this execution policy is logging execution policy, but it also has inside this margin execution policy that we're going to be using now. And we're going to forward the request to margin execution policy. Our request was to execute orders. This is the request we're receiving from the book. And we can see the logic here is very complicated. So we can track it down and say, okay, so we have aggressor margin mute execute order begin. We have book margin mute execute order begin. So we have margin of the aggressor, and we have margin of the book order. So there is these two parties, right? So there is this trader A and trader B. Trader A has some accounts, trader B has some accounts, so we have different accounts for those traders. And now we have to begin transaction between these two. So we have to say begin transaction on trader A and begin transaction on trader B. So we begin the transaction on both accounts. And then we say, okay, now we're going to commit. If the begin is successful, we commit. So this begin actually does the whole logic to lock quantities whatsoever, to calculate if it is possible to execute. If begin returns yes, it's good to go. Then you see we have two begins. So those begins will start a transaction on both accounts because we have two of them. Each of them will check those accounts if there is enough margin for the trade to happen. And then if they are successful, if they say, yeah, it's good to go, the trade can happen. And in this implementation, trade can always happen. I never check if your portfolio has enough assets or if there is enough margin. Margin calculations are very complex. I didn't include them in this example. So I'm just allowing for you to always go on margin, okay? So we're good to go. And the next step is to commit, right? So we approve this transaction, we commit the transaction, and now we have to commit both accounts. And we have a situation when we committed the first account, right? So we committed the first account was okay, but the second account was failure of commit. So we have to roll back the first account because the execution was unsuccessful for whatever reason. I don't know, database failure, for example. Okay, so this is the whole workhorse of actually creating a trade in the system, because we only did a match so far. That was like a front end of the book, but this is the back end of the execution mechanisms. Okay, so what happens when I do execute or the commit? So what does this commit do? So you can see that the commit takes the quantity that was executed, and then it takes both orders, the order that's on the book and the order which is being executed here. Okay, so let's check again. We commit for both accounts. So you can see that one account is aggressor account and it is aggressor order. So we have aggressor order against book order, but the second commit is a book order against book order. Okay, it's not really against, it's not really against, it's just this execute order commit requires a book order against which we are executing, and then the order, the leg of the order, right, that we are executing, okay? Because for the book order, we're gonna take the price, okay? So the aggressor order may have limit price, but it is not at the price at which we're executing. We always execute at the price of the book order. So you can see we take the price of the, we take the limit data of the order on the book, right? And it has to be a limit order. It cannot be immediate or cancel because orders on the book are limit orders. Now, the side is gonna be either the side of a limit order or the opposite side of a limit order if I'm the aggressor, right? So we also have here Boolean saying we are the aggressor. So again, when we are processing aggressor account, we're saying aggressor is true. If we're processing book order, aggressor is false. Okay, so we have our book order limit price from this limit here. And we have the side, okay, of the order, whether it's aggressor or not, okay. Now we take the base symbol and quote symbol, so we take them from market that was traded on, okay. And we need to find the accounts, the sub-accounts for those assets. So remember, every account, trader 1 and trader 2, these are the accounts. They have sub-account, a sub-account for an asset. So trader 1 may have Bitcoin, may have Ethereum, may have dollars. These are sub-accounts. So we need to take the sub-account. If a transaction was Bitcoin, Ethereum, then we need to take the sub-account for Bitcoin and sub-account for Ethereum, right? So we have two traders, two transactions, and at the same time, each transaction has two legs. So altogether in our system, we're going to process 4 legs for one trade. Here we're doing a very smart thing. I'm going to talk about it later. This is a magical function to calculate the value of an order. So basically, we multiply quantity by the price to calculate the value of the order in the quote currency. However, I'm using a specific way of dealing with decimal places. As I said in the beginning, different markets and different assets have different number of decimals assigned, and I have to deal with the difference between the same asset having different decimals on the market and different on the asset, right? So this one function is doing this magic inside, okay? Let me just show you this function. So this function is gonna call calculate value and change decimals, okay? And calculate value is gonna use polynomial evaluation of a multiplication. So we want to lose the minimum amount of precision here. We don't want to lose any precision. So this is why I'm decomposing my decimal into a polynomial. So you can see here, these are the equations I have derived, okay? And this is my final calculation. You're free to look at my repository on GitHub and walk through this in your spare time. All right, so now we need to choose which side we are on. Is it bid or ask, okay, for this order? And if it's an ask, so if it's an aggressive order, ask would mean sell, I'm selling. If it's a book order, ask would mean ask side. So I'm selling, but I'm ask side, right? So if I am selling, then I'm delivering a base asset, okay? So if it was Bitcoin, Ethereum, then Bitcoin is the base asset, Ethereum is a quote currency. So I'm delivering Bitcoin, right? If I'm selling Bitcoin, I'm delivering Bitcoin. But in return, I have to receive Ethereum, right? So I'm committing receipt of Ethereum. So you can see that we have a sub-account for Bitcoin, and I'm committing delivery of Bitcoin to that account. And I have a sub-account for this Ethereum, for the quote currency, and I'm committing the receipt to this account, right? Let's see what one of those two commit functions really do. So let's look at the commit deliver, for example. So you get the quantity that was delivered, okay, to this sub-account. So this is margin asset account, so that sub-account for asset. So we first match lots, and then we create new lots if there is anything available. So you can see the match lots. So on the received side, okay, so we deliver. So if we deliver something, then we first check if we have it in our received lots, if we received it in the first place before, right? So if I'm delivering a Bitcoin, do I have any lot of Bitcoin on the received side? Received side is the long side, okay? And deliver side is the short side, okay? So if I have something, it's on the long side, I have received it. So I need to check if I have received something that I can now deliver. So that's why I'm doing match lots on the receive side. So maybe it's the case that the quantity I need to deliver is 5 Bitcoin, and I only found that I have only 2 Bitcoin on my receive side. So, there is quantity left, 3 Bitcoin. What do we do with this quantity left? We create new lot on the opposite side, right? We create it on the delivered side. So we need to deliver this 3 Bitcoin that we didn't match against our long side. So we put it on the short side, okay? So we have a lot on the short side that we need to deliver this Bitcoin, that we need to deliver this 3 Bitcoin. We also remember the price at which we were delivering it, right? So that when we calculate our gains, we know that, okay, we were short this amount of Bitcoin. This was the price, they paid us. And if we now receive Bitcoin so that we can cover for it, we can check the difference in price and see if we made any loss or gain, if we made any gain or loss. So this is why we would have price here. All right, so what does the lot matching look like? So this is our lot matching function, okay? And lot matching function is calling match lots and tell, and then it calls the callback. So let's go to this one. So this is our lots matching function. It takes the quantity that we want to match against, okay? And some details for our transaction that we want to store in the lot, okay? So we can see that the lot has the quantity that was originally there on the lot when it was created, quantity that's left after all the transactions with this lot, and the queue of transactions that happened to this lot. And this is the transaction that could happen to a lot. It has an order that caused the transaction. It has the executed price so that we can later calculate the P&L. And we have also executed quantity if we wanted to know how much of the lot was consumed by this transaction. So our match lots function is using Rust magic. So what do we do here? We use fold while. Okay, we fold while. We take the open lots. What is open lots? So we can see that the side on an account, so we have long and short, or deliver and receive. We have open lots and closed lots. So open lots is what we currently have on our side, and closed lots is everything that's gone, that we don't have it anymore, okay? So we use fold while on the open lots. So we go over open lots, starting from the oldest lot and going through the lots to the newest lot, and we consume those lots using this fold while. So fold while will just iterate, okay? Fold while will just iterate. And we use this continue and done from itertools that control the fold while, so that we can break. It's a while not done. So that's how it works. And in this fold while, we close quantity on every lot that we go through. And this close quantity will return to us what is the quantity left that we didn't close in this lot. So close quantity on the lot will return to us the amount of quantity that was in excess of what was available in the lot. So if lot was 5 and we tried to close 20, 15 is the excess. So if there is an excess, we continue and we go to the next lot and we match this 15 against the next lot. If there is no excess, we finished, right? And we say no excess. Now this fold while returns a struct fold while which has is done, okay? So is done will tell us if we reach this branch or not. And this is critical because then, depending on whether it is done or not, we will know if there was a partial match or not. And we return this to the caller so that the caller will know if the first entry of the open lots has been partially matched or not. Now we take the result, okay, of this fold while. So the result is here, it's a tuple, it's a position and the quantity that was in excess, okay? And we take this position and we drain the lots until this position. So position, as you can see, we increment it every time we have excess. So we go through lots. So if we have excess after we close first lot, the position becomes 1 and so on. And then it becomes 2 and so on. So we drain all the lots that are fully closed. We drain them and we put them into the closed lots. So that's a very neat way of moving lots, some portion of lots from one queue to another queue, okay? And then we return this tuple saying, did we have the partial match? What was the position at which we drained? And how much quantity is in excess, okay? And we can see that this match lot switch callback is calling this match lot tel, okay? It's getting this tuple, and based on the fact whether there was a partial match or not, it will call this callback on this extra lot that is in front of the open lots, right? If there is a partial match on the first lot of the open lots, we call the callback on this partial match. And in my example, I have connected a print message to this callback so that we see when the lots get closed. And then we call callback for all the closed lots. Because we know how many lots were closed, we can go to the back of our closed lots queue and take this number of lots from the back and call the callback on those lots. I'm iterating over them in reversed order, meaning that I'm starting from the back, and then I move back by the number of lots that I closed, and then I reverse the iterator once more, and I go forwards, and I call callback on those lots at the end of the queue. So this is my way of saying, call me a callback on the last pause lots in this closed lots, okay? So this way, we matched some lots, we closed them, we created the transactions for the lots, and we're now very happy, right? Our commit delivery called match lots with callback, okay? Passing in this callback here, event handler, that's passed in here. So we have this margin lot event handler that has handle lot closed and handle lot opened. So that is called when there is some excess of quantity and we need to create a lot on the opposite side. So create lot with callback. Let's see this one. This function is straightforward. We just create a lot with given quantity. And we call the callback on that lot. So you can see how simple is the logic of the lot matching when you write it in Rust, right? Everything is logical. Everything is like split into little bits, little pieces. So you have like the margin manager, which manages all the user accounts. Then user account has subaccounts for assets. Then each asset has, received and delivered side, and each side has a queue of lots that are open and a queue of lots that are closed. And then each lot has a queue of transactions that happen to this lot. So we have this very nice tree of, topology of our system. So when it happens, now we can calculate using all this data our gains and losses. By using this transaction data, we have the quantities and prices. We can see how prices were changing, what we're buying, what we're selling, what was the difference in price using those lots. And we can go back to our call side of this. So we're committing the delivery and received, right? And the next thing that happens is just, okay, we just finished. Okay, so we go back to our order book. And the next thing we're going to do is we're going to use market data policy to tell the market data policy that we have executed something. Handle order executed. So now we're going to market data policy and telling, hey, there was an order that was executed. And market data policy can publish it back to the users who subscribed to this market data. All right, so this is our Exchange implementation in Rust. And it's very straightforward and simple. We have our user, they send an order, order manager takes the order, finds the book matches that order against the levels. If there is a match and execution happens, we go to execution policy, which goes to the margin. Margin is managing the accounts, And on the accounts, we create some lots, we match some lots. And then control goes back to the book, which talks to the market data policy, which sends back the market data to all users. And at the same time, execution policy would send back the private information about executions to the users that originated the orders. Alright, so this is my implementation of the exchange in Rust. And it's very straightforward and quite simple. I encourage you to browse the code in your spare time. The code is available on my GitHub in a repository called Benthic. Why Benthic? It's Benthic because Benthic is the bottom of the sea and the place where the crabs live. Okay, so this is my Exchange implementation in Rust. Comment, like, subscribe, and stay tuned for more cool videos. Ciao!